Imagine standing beneath a city where millions of people rush above your head every single day. Now picture a steel monster longer than 2 football fields, weighing more than 2,000 tons, silently carving a perfectly round tunnel through solid rock and clay with millimeter precision. You never see it, you never hear it, yet it changes the future of entire cities. But here's what nobody tells you. Before this incredible machine ever touches the ground, it begins a journey that stretches across continents, mines, steel mills, and some of the most advanced factories on Earth. Most people call it a tunnel boring machine, or simply a TBM. But think about this for a moment. The largest models stretch well over 120 meters, their cutter heads can exceed 17 meters in diameter, and each rotation crushes rock that took millions of years to form. Every meter forward demands enormous power, flawless engineering, and thousands of perfectly manufactured parts working together without hesitation. And what happens inside the factory before this giant is born is even more astonishing. Over the next few minutes, we're going behind the scenes of one of humanity's greatest engineering achievements. You'll follow every piece of raw material from the Earth itself, watch molten steel become precision components, witness robots and master craftsmen working side by side, and discover how engineers guarantee that a machine buried deep underground simply cannot fail. By the end, you'll never look at a subway system the same way again. Every tunnel machine starts with one material above all others: steel. High-grade iron ore arrives from enormous open-pit mines in Australia, Brazil, Canada, Sweden, and South Africa. Some deposits contain more than 65% iron, making them ideal for producing the ultra-strong steels required for the cutter head, main bearing housing, and structural shield. Every ton begins its life blasted from ancient rock using explosives powerful enough to shake the ground for kilometers. The freshly mined ore travels an astonishing distance before reaching a steel mill. Giant haul trucks carrying more than 300 tons dump their loads into crushing plants. Conveyor belts stretch for kilometers, while freight trains nearly 3 kilometers long transport the concentrated ore toward deep-water ports. From there, bulk carriers crossing entire oceans deliver millions of tons of raw material to steel producers around the world. But steel alone cannot survive the punishment waiting underground. That's why manufacturers carefully blend chromium, nickel, molybdenum, manganese, vanadium, and other alloying elements into specialized steel grades. These elements dramatically improve hardness, fatigue resistance, corrosion protection, and impact strength. Most people never think about it, but a single tunnel machine may contain dozens of different steel alloys, each designed for one specific job. Then come the cutter tools, the teeth that actually attack the rock. Their secret ingredient is tungsten carbide, one of the hardest engineering materials on Earth. The tungsten often begins in mines located in China, Vietnam, Portugal, Bolivia, and Rwanda before undergoing complex refining and powder metallurgy processes. Without these incredibly hard cutting discs, even the world's largest tunnel machine would struggle against granite and quartz-rich formations. Hidden inside the machine are kilometers of copper cable carrying electricity, data, and sensor signals. Much of that copper begins in massive mines in Chile and Peru, where ore is crushed, concentrated, smelted, and refined until it reaches more than 99.99% purity. Every motor, every sensor, every control cabinet depends on that remarkable conductivity to keep the giant moving safely beneath crowded streets. The hydraulic system tells another remarkable story. High-strength cylinders, forged steel rods, precision seals, and thousands of liters of hydraulic oil generate the force needed to push thousands of tons forward through solid earth. Some hydraulic components operate under pressures exceeding 350 bar, producing forces powerful enough to move entire buildings if applied above ground. Yet underground, that immense strength must remain perfectly controlled every second. Even the rubber seals deserve attention. These massive circular seals keep groundwater, mud, sand, and abrasive particles away from the machine's most valuable bearings. Manufacturers formulate specialized synthetic rubber compounds that resist extreme pressure, temperature changes, chemical attack, and constant friction for years beneath the surface. A seal only a few centimeters thick can protect machinery worth tens of millions of dollars. Building one tunnel machine also leaves a significant environmental footprint. Mining, steelmaking, shipping, and heavy manufacturing consume enormous amounts of energy and generate substantial carbon emissions. That's why manufacturers increasingly rely on recycled steel, electric arc furnaces powered by renewable electricity, and optimized logistics that reduce waste without sacrificing strength. Every improvement matters when a single machine can contain more than 2,000 tons of material. By now, millions of dollars worth of steel, tungsten, copper, rubber, electronics, and hydraulic components have completed a journey spanning thousands of kilometers. Every shipment arrives at precisely the right moment because a single missing part can delay an entire production schedule. But here's the mystery that keeps engineers awake at night. How do thousands of individual pieces become one underground giant capable of digging through mountains without losing its way? That's where the real manufacturing story begins. The journey starts with steel plates that can exceed 150 millimeters or nearly 6 inches in thickness. Computer-controlled plasma and laser cutters slice through the metal with temperatures reaching nearly 20,000 degrees Celsius, or over 36,000 degrees Fahrenheit, while positioning accuracy stays within fractions of a millimeter. Molten sparks spray across the workshop like bright orange fireworks, and the smell of hot steel fills the air. In only a few minutes, a flat plate begins its transformation into part of a machine that may tunnel for years. Those freshly cut sections move into gigantic rolling machines capable of bending steel with forces measured in thousands of tons. Hydraulic rollers slowly curve the plates into perfectly circular segments that will eventually form the machine's protective shield. The process takes several minutes for each section, and laser measurement systems constantly verify the curvature. Even a tiny deviation could multiply into major alignment problems after final assembly. Next comes one of the most demanding operations in the entire factory: welding. Multi-pass welding robots join enormous steel structures using temperatures above 6,000 degrees Celsius, or nearly 11,000 degrees Fahrenheit, at the electric arc. Some weld seams stretch for several meters, requiring hours of continuous work to complete. As sparks explode across the workshop and the smell of heated metal lingers in the air, every weld must penetrate deep enough to become as strong as the surrounding steel itself. After welding, the giant structures don't move directly to assembly. They enter massive stress relief heat treatment furnaces, where temperatures commonly reach between 550 and 650 degrees Celsius, or roughly 1,020 to 1,200 degrees Fahrenheit. The steel remains inside for several hours before cooling slowly under carefully controlled conditions. This process releases internal stresses created during welding, reducing the risk of distortion once the machine begins pushing against solid rock. Then engineers install the machine's most expensive single component, the main bearing. Some bearings measure more than 5 meters in diameter and weigh over 100 tons. Precision cranes lower the enormous ring into position so slowly that the movement almost looks frozen in time. Specialized hydraulic tools tighten massive bolts with carefully controlled loads measured in thousands of kilonewtons, ensuring the bearing distributes tremendous forces evenly throughout the structure. Now the cutter head itself finally comes alive. Workers mount dozens of disc cutters made from tungsten carbide, each weighing hundreds of kilograms. Every cutter must rotate freely because friction generates tremendous heat while crushing rock. Imagine hearing the metallic click of every fastening bolt echo through the enormous workshop, knowing each one will soon face pressures strong enough to fracture granite. Attention then shifts toward the machine's powerful hydraulic system. Hundreds of cylinders, pumps, valves, and high-pressure hoses connect like the arteries of a living creature. Before installation, technicians pressure test every hydraulic circuit at well above its normal operating pressure, often approaching 525 bar or around 7,600 psi, to guarantee absolute reliability. Even the smallest leak could become a major problem deep beneath a city. At the same time, electricians weave kilometers of copper cable through the machine's enormous body. Thousands of sensors, Cameras, laser positioning systems, electric motors, and computerized control cabinets gradually come online one by one. Bright indicator lights begin flashing across the control room, replacing silent steel with the first signs of intelligence. What once looked like an empty shell now starts thinking before it even moves. Finally comes the moment everyone has waited for. Engineers activate the completed cutter head for its first factory rotation at low speed, while technicians monitor vibration, temperature, hydraulic pressure, electrical loads, and bearing performance in real time. The deep mechanical rumble echoes through the building as thousands of perfectly synchronized components come to life for the very first time. But here's what surprised even experienced engineers. The real challenge hasn't begun yet, because before this underground giant earns the right to dig beneath the city, it must survive some of the toughest tests modern engineering can invent. Before a tunnel-boring machine ever disappears beneath the city, engineers treat it like an aircraft preparing for its very first flight. Every bolt, every bearing, every hydraulic cylinder, and every electrical connection must prove it deserves to be there. Think about this. Repairing a faulty component hundreds of meters underground could cost millions of dollars and delay an entire metro project for months. That's why the most important digging happens long before the cutter head ever touches rock. The inspection begins with robotic laser metrology systems that scan the entire machine from thousands of angles. Blue laser beams sweep across the cutter head, shield, and structural frame, creating a digital twin accurate to within about 0.05 millimeters, thinner than a human hair. Millions of measurement points appear instantly on giant screens, revealing even the smallest distortion invisible to the naked eye. What looks perfectly round to us can still fail the computer's relentless inspection. Then, artificial intelligence joins the inspection. High-resolution vision cameras examine every weld, bolt, hydraulic fitting, and machine surface, comparing them with thousands of reference images collected from previous projects. The software can identify tiny cracks, incomplete weld penetration, surface defects, and incorrect bolt placement within seconds. Most people never think about this, but an AI system never gets tired, never loses concentration, and never blinks. Some defects hide deep inside the steel where no camera can see them. That's when technicians use ultrasonic testing, sending high-frequency sound waves through thick metal to reveal hidden cracks or internal voids. Other teams rely on magnetic particle inspection, where magnetic fields and fine iron powder expose invisible surface fractures almost like magic. A weld that appears flawless can still fail these demanding examinations, and if it does, it gets repaired before production continues. Next comes pressure testing, and the numbers become extraordinary. Hydraulic systems operate at pressures exceeding 350 bar, while test rigs often push them significantly higher to verify a comfortable safety margin. Every cylinder extends and retracts hundreds of times as sensors watch for microscopic pressure drops or temperature changes. The deep hiss of hydraulic oil rushing through the system fills the factory, reminding everyone that this machine must perform perfectly day after day beneath thousands of tons of earth. Now the cutter head finally earns its reputation. Massive electric motors slowly accelerate the enormous rotating face, while vibration sensors monitor every movement in real time. Precision accelerometers detect vibrations measured in microns, allowing engineers to identify and balance long before it becomes dangerous. Imagine hearing the low mechanical thunder as hundreds of tons of steel rotate with incredible smoothness, almost as if the giant machine were floating on air. Even after all that technology, one inspection still depends entirely on human experience. Veteran engineers walk around the completed machine, listening carefully as it operates. They recognize subtle sounds, a faint metallic tap, an unusual vibration, or a change in hydraulic tone that sophisticated computers sometimes overlook. Decades of experience become an instrument more sensitive than any electronic sensor, proving that human skill still holds a place beside the world's smartest machines. Manufacturers also perform endurance testing that simulates months of underground work in only a fraction of the time. Motors run continuously, bearings remain under heavy load, hydraulic systems cycle thousands of times, and electronic controls process endless streams of sensor data. Temperatures, vibration levels, lubrication flow, and electrical consumption stay under constant observation. By the end of these demanding trials, engineers know exactly how the machine behaves before it ever reaches a construction site. Only after passing every inspection does the machine receive final approval. International quality standards such as ISO 9001 guide manufacturing processes, while project-specific customer requirements often demand even stricter verification. Despite thousands of inspections, rejection rates for individual critical components still remain low because defects are caught early instead of late. That relentless attention to detail explains why these underground giants can operate reliably for years in some of the harshest environments on Earth. At last, the machine is disassembled into transportable sections, loaded onto heavy-haul trucks and cargo ships, and sent toward its destination, somewhere beneath a growing city. But here's the question almost nobody asks. Once these incredible machines leave the factory, how many are built each year? Which countries dominate this remarkable industry? And what astonishing facts reveal just how important tunnel boring machines have become to the modern world? Those numbers are even bigger than the machines themselves. Once a tunnel boring machine leaves the factory, it begins a journey almost as remarkable as the one that created it. Unlike cars or smartphones, these giants are not built by the millions. Worldwide, only a few hundred large tunnel-boring machines are manufactured each year, yet each one represents years of engineering, thousands of precision-made components, and investments that often range from $20 million to well over $100 million, depending on size and project requirements. Every machine is closer to a custom-built engineering masterpiece than a mass-produced product. The global tunnel boring machine industry now generates an estimated $6 to $8 billion annually, driven by expanding metro systems, railway tunnels, highways, water transfer projects, and utility infrastructure. Cities continue growing upward, but transportation keeps moving underground where space remains available. Every new metro line, flood control tunnel, or high-speed rail project increases demand for bigger, smarter, and more efficient machines. As urban populations climb, the hidden world beneath our feet becomes more valuable every year. Today, 5 countries dominate this remarkable industry. China accounts for roughly 45% of global production, fueled by enormous domestic infrastructure programs and large-scale manufacturing. Germany follows with world-renowned engineering expertise, while Japan continues pushing precision and reliability to extraordinary levels. The United States and Italy also play major roles, producing highly specialized machines for complex geological conditions around the world. Behind every machine stands an army of skilled people. Worldwide, hundreds of thousands of workers contribute to tunnel boring machine production through mining, steelmaking, forging, machining, electronics, hydraulics, software development, transportation, and final assembly. Many never see the finished machine, yet their craftsmanship travels beneath cities across the globe. Most people never think about this invisible workforce, but without them, modern underground transportation simply could not exist. The story of tunnel boring machines stretches back more than 150 years. Early mechanical tunneling attempts struggled with unreliable cutters, weak materials, and limited power. Everything changed during the second half of the 20th century as stronger alloy steels, computer controls, hydraulic technology, and precision manufacturing transformed experimental machines into reliable engineering giants. What once took years of dangerous manual excavation can now be completed faster, safer, and with astonishing accuracy. Now, imagine what comes next. Engineers are developing smarter machines capable of analyzing rock conditions in real time, adjusting cutter head performance automatically, and predicting maintenance needs before failures occur. Artificial intelligence, digital twins, autonomous guidance systems, and advanced sensor networks promise to reduce costs while increasing safety even further. Within the next decade, tomorrow's tunnel machines may make today's engineering marvels look surprisingly primitive. Did you know that the largest tunnel boring machines have cutter heads wider than many two-story houses are tall? Did you know some projects require these machines to operate continuously for years before reaching daylight again? And here's perhaps the most astonishing fact of all. When one of these giants finally completes its mission, Engineers often dismantle it deep underground, transport the pieces through the very tunnel it created, and rebuild it somewhere else to begin the entire adventure again. From iron ore blasted out of ancient mountains to precision-machined steel assembled by master engineers, every tunnel boring machine tells a story hidden beneath our cities. Every weld, every sensor, every cutter disc, and every bolt exists for one purpose: to build the underground pathways that millions of people depend on every single day without ever seeing the extraordinary technology behind them. The next time you ride a metro train, remember that somewhere beyond the tunnel wall, a masterpiece of engineering once carved that path through solid earth, centimeter by centimeter. The next time you hold one of these in your hands, remember, it didn't just appear. It was born from the earth, shaped by fire, perfected by technology, and approved by the strictest standards in the world. That's not just a product. That's a masterpiece of human engineering. If you want to go deeper into the hidden world of manufacturing, tell us in the comments what product you'd like to explore next. Like this video, subscribe to the channel, and we'll see you inside the next factory.